This is going to be a short video, okay? Most books include a brief introduction to quantitative analysis in the stoichiometry chapter, and I think that's a great idea. Don't get me wrong, because I've told you before, students panic with names. So quantitative analysis, titrations, combustion analysis. Combustion analysis actually in this book was found here. I just moved it to the video where we was doing the empirical formulas because it made sense to put it in there. But you have a number of techniques in here, and just the names make people freak out. And I always tell them, if you stop to think about it, if you forget about the names, it's nothing more than another simple stoichiometry problem. That's why it's very fitting that it appears in the stoichiometry chapter. Basically, the idea of this video is to convince you that if you can do stoichiometry, you can do quantitative analysis. The idea is to determine the amount or the concentration of a substance in a sample. And we're going to look at two different techniques, titration and gravimetric analysis. But once again, remember, the actual calculations is nothing more than stoichiometry. Fancy names? Yes, because they have been using chemistry for a long time, and they were given names a long time ago, and chemists are very much, this is what we've always called it, so we are going to stick with it. But it's still nothing more than more stoichiometry. Titration is when you have a solution that you don't know the concentration. So you have to have a solution that you know the concentration, and we call that a titrant, and the analyte is a solution that you don't know the concentration. You're going to make them react, and you get a complete reaction, and we'll discuss in a moment how do you know you got a complete reaction. We call that the equivalence point of the titration, and that allows you to calculate the analyte concentration. Very typical reaction I give my students. You have certain volume of hydrochloric acid, they don't know what the concentration is. You get a little burette that has, I usually give them 0.01, I'm making up numbers, molar sodium hydroxide. So they're going to be adding sodium hydroxide drop at a time until all of the hydrochloric acid reacts. And how do you know that? We'll cover it in a second, okay? But once you have the reaction, if you know the volume that you use and you know the concentration, you know how many moles, so you know how many moles of hydrochloric acid, so you can calculate the concentration because you knew the volume. It's, again, stoichiometry. Nothing special. The key is knowing that the reaction reaches completion and don't overdo it. So we add an indicator. An indicator usually changes color if it's not the equivalence point very, very close, okay? The volume that you measure, or the volume at which you get the color change, is actually the endpoint. But you find an indicator that the endpoint and the equivalence point are very, very close together. And we'll cover a whole lot more in the second semester of chemistry, but there's actually a big table of indicators, so you know what reaction you have, and you can choose the proper indicator. Okay? So we're talking about hydrochloric acid and sodium hydroxide. So you have a volume of 50 milliliters of hydrochloric acid. And you reach the endpoint, usually you put a dye in there that is clear in an acidic solution, but it turns pink the moment it goes above pH 7. The moment it's more than neutral. So it took 35.23 milliliters of sodium hydroxide of this concentration. So you want to know what was the concentration of the hydrochloric acid. Okay? Well, here you have the equation. You see the mole ratio is 1 to 1. So from the volume of sodium hydroxide and the molar concentration, you can determine how many moles. Remember, molarity is number of moles divided by volume in liters. Don't forget that. Okay? Once you know the moles of sodium hydroxide, let me call it by my preferred term, look at the mole ratio, you figure how many moles of hydrochloric acid. When you know how many moles of hydrochloric acid and you knew the volume because it was given to you, you can calculate the concentration. Very simple. Let's do the actual calculations. So first you get the sodium hydroxide and you change it to liters. Okay, so you have liters. The concentration, this is 2.50 moles per liter. So liters cancels out, so you know how many moles of sodium hydroxide. We said the mole ratio is 1 to 1. 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide, so moles and moles cancels out, and that tells you how many moles of hydrochloric acid you have. You know the volume, so the molarity of hydrochloric acid is the number of moles that you got in here, times the volume that we are going to change to liters. So moles per liter, that's molarity. And you could ask in here, how do I have 3 significant figures? My first number had 4. Well, the molarity had only 3 significant figures. So you carry 3 significant figures all along, your answer has 3 significant figures. This is very simple. Some of you, and we'll cover that because we'll do a lot of titrations in college chemistry too, but some of you learn in high school the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And you use that equation all the time. Never. Okay? I don't know why high school teachers do that, but so many of them, it drives me insane. That's correct when the mole ratio is 1 to 1, but that's not always going to be the case. If I use sulfuric acid, if I have sodium hydroxide and sulfuric acid, I'm going to need 2. So the mole ratio is 2 to 1. What if I use calcium hydroxide and phosphoric acid? I'm going to need 3 of these and 2 of these. The mole ratio is 3 to 2. So if you do it like it is a stoichiometric problem, you will include the mole ratio and you get the right answer. If you use that formula that I like so much in high school, you will be wrong roughly 2/3 of the time. That's not satisfactory. Wrong 2/3 of the time? I did my calculations looking at problems and actually counted the number of problems, and that's an approximation, but yes, comes out something like that. I'll say 50%, that's not satisfactory. But when you talk about you're right only 33% of the time, it's like, why would anybody do that? So if you learn that in high school, forget it. This is a stoichiometric reaction. You do it the same thing that you did in the previous video, and you always come up with the right answer, 100%, not 33%. Gravimetric analysis is another type. When you have a mixture, sometimes you can separate the substance you're looking for, the analyte, by causing a physical change that allows you to isolate it. Okay? Most of the time, what they do is cause it to precipitate, do a chemical reaction, you cause it to precipitate, because then you can filter it and you know how much you have. So obviously what you filter is the result, but let's do an example showing you. So you have so many grams of a mixture, and some of the mixture is magnesium sulfate. Okay? So you want to know how much magnesium sulfate there's in the mixture. Well, how do you know? Well, if you dissolve it and you make it react with barium nitrate, that causes barium sulfate to form, and that, looking at solubility table, it precipitates. So you filter it, you dry it, obviously, and that's how much barium sulfate you got. So from the mass of barium sulfate, you calculate moles, don't forget. Again, call it mole ratio. I really prefer that. Okay? Moles of barium sulfate versus moles of magnesium sulfate is a 1-to-1 ratio. So you determine the moles of magnesium sulfate from there. Now, they're not asking you how many moles, you need to change it to grams. Be careful. Is that what they're asking you? No. they're asking you what is the mass percent. What is the mass percent? It's the mass of sodium sulfate divided by the total mass. So once you have this mass, you can calculate the percent. A lot of people stop here and they're so proud. Hey, I remember to change it to moles. I remember to use the mole ratio. I remember to change it to grams. Yes, but that's not the question. You stop too soon. Read the question, okay? So we do the calculations. Your grams of barium sulfate, you change into moles. Grams and grams cancels out. The mole ratio we say was 1 to 1. So moles of barium sulfate cancels. Now you change moles of magnesium sulfate to grams. Moles and moles. So that's how many grams of magnesium sulfate you have. What was the mass of the sample? It was given to you in the problem. Remember? Here at the beginning, they tell you how much the mixture was. So you divide the moles of magnesium sulfate, but the weight of the sample that was given in the question times 100, that is your percentage. Again, don't stop here. If it's me, I'll say, okay, you did 1, 2, 3 steps out of 4, I'll give you 3/4 of the credit. But the Irish instructor who will say, no, I'm asking for percentage, you give me something else, and they won't give you any credit at all. I don't know your instructor. But even 3/4 of the credit is not as good as the full credit when the only problem is that you did not read the question. This is a perfect example why you need to read the question, answer what they're asking you. Don't stop too soon. So I told you it was going to be a very short video. I have practice examples. So once again, if you make an appointment through Wisant, and the link is in the video description, I'd be glad to share these worksheets so you can practice until you can do all the questions right before you take an exam that's going to be great.